These are my solutions to the conceptual questions out of chapter 22 for AP Physics 2. So for question 5, you were given a diagram like this. It was symmetrical in nature, so the wire was made of the same material and blah, blah, blah. So therefore, it was asking to rank the currents. Here, I1 would equal I4, and those would be greater than I2, which would equal I3. So if these are the same lengths of wire, made of the same material, same type diameter wire, what have you, that means they'd have the same resistance on each side, so the current would split evenly, which is why I2 equals I3. If this side had a shorter length of wire, the resistance would be less, and more than half the current that splits off from I1 would go in this direction. But as it is, it splits evenly, comes back together in I4. Q9 is asking about electron current. You have to assume a non-ideal wire here. If you didn't, the answers to these questions, or the questions, really don't make sense. So you have a battery that drew a wire. If we're thinking about electrons are negative. They'd be attracted to the positive terminal of the battery. So the flow in this circuit is going to be counterclockwise. The electric potential won't change much in the wire, but it would have to, well, at any given length, but it actually has to decrease overall because as you go in a complete loop, you're going to have to gain electric potential as the electrons go through the battery. You have to lose it as you go through the wire. So that was a little sneaky, I thought. It should have just told you it was a non-ideal wire. Letter C, where does the energy go that gets lost, or the electrical potential? And it actually goes into those tiny little collisions that heat up the wire. So it basically goes into thermal energy. For letter D, in the battery, the electron have to move down the battery to complete the closed loop of the circuit. So when that's happening, and this is letter E, you actually have an increase in electric potential energy, since the chemical energy stored in the battery is converted to electric potential energy. So this is where you would have a charged escalator. It's a little weird in this picture because we see the electrons going down, but the chemical reactions will essentially increase the energy per charge of those electrons. And for letter F, where does that energy come from? It comes from stored chemical energy. I'd said that earlier. Number 10 is the ranking the resistances of these. So we're assuming they're all the same material. You would use this, which is your resistivity formula. Resistance of a wire is equal to resistivity. That's the Greek symbol rho. It looks like a lowercase p, multiplied by the length of the wire divided by the area of the wire. Well, you're not given the area of the wire directly, but you are given the radius. The radius is proportional to the area is proportional to the radius squared. So I just did some little simple maths here. I took this length as being one length on top. The resistivity is the same for all of them, so I ignored that factor. The radius here is 1, so I'm going to divide it by 1 squared. So 1 divided by 1 squared gave me 1 unit of resistance. Here, this wire is the same length, but it has twice the radius. So I'm going to take 1 and divide it by twice the radius squared, and that's 1/4 the resistance. So proportionally, wire 2 has 1/4 the resistance of wire 1 because it's a wider wire. Basically, there's more room for the electrons to flow through. Wire 3, twice as long and twice the radius of the original one. Mathematically, that comes out to half the resistance of the original one. Wire 4 comes out to 4 times the resistance of the original one. And wire 5, which is 4 times the length and twice the radius, actually comes out to the same resistance as wire 1. So we get that R4 is greater than R5, which equals R1, is greater than R3, is greater than R2. Question 15 is asking you to rank the currents through these wires. All we have to do here is use Ohm's law. I is equal to the change in voltage divided by R, or change in potential divided by resistance. We're given the resistances. We're given the delta V, or change in voltage. All I've got to do is solve for that. Ends up that wire 3 has the most current. I think I said something earlier wrong there. But this has the most current, 2 volts divided by 1 ohm. The first one and the fourth one are the same, and the second one is the least amount of current. So here, if we do assume ideal wires, so that is different than question 9. If we do assume ideal wires, then we're going to assume that all the resistance is here. So I drew some points here. I said F, A, B, C, D, and E. Now they're different distances apart, but I'm showing them as this kind of like this on the graph. So as the charge goes around a circuit here, we're saying that it's going to gain potential as it goes through the battery to A, and then to B, and then to C. So I have those as three little stair steps, each with one EMF of voltage. I should have labeled that axis R. Maybe I will. Maybe I will. I'll say potential volts. Put that over here. And the little steps here, I basically assume that there wasn't any charge escalator at the little nubs on the battery. This region of the wire, if it's an ideal wire, we have no loss of potential. It takes no effort to get through there. Here, through the resistor, there is a massive loss of potential. In fact, it's all the potential is lost there between D and E. And again, as we go from E to F, if it's an ideal wire, we'll lose no potential. So think about how this might differ if these were not ideal wires. I can tell you what I think might be a little different between C and D and E and F. Further, question 22, this relates to the power formula. P equals V times I, or I equals P divided by V. We can use that to figure out the current of each of these, and therefore bulb B had the most current. For number 24, a longer, skinnier wire, and this is basically asking what would stretch out if you had a wire that was stretched out, would have more resistance. But this is actually asking about the resistivity of the material. That would not change. The resistivity itself is a property of the material. It's what's called an intensive physical property. So it is not quantity dependent. Here we've got three different parts of wire: wider, skinny, medium. The current has to be the same through all three. I see only one path for the electricity to flow, and therefore I don't see any other way. Draw a little arrow there in any of those three spots where that's going to end up having a different amount of current. So there's one path. It's a series circuit. Hopefully those made sense, and we'll discuss them in class.